So now we go to see about the characteristics of flames. Okay. So let us first see the characteristics of the turbulent premixed flames. Okay. So now consider a laminar premixed flame which has a thin flame zone. So the flame zone is considered thin because it is having a thickness of say 1.5 2 mm, something like that. So let us just draw a flame like this, a conical flame at the end of Bunsen burner, which will be very thin in this. So this is the flame what we get in the laminar regime. So this is the flame we are going to get. So it is very well behaved and a thin flame, and if you take photography as a function of time, there will be not much variation in this shape, and the flame is intact. We are talking about a stable flame basically. However, when the flow becomes turbulent, eddies of different sizes are involved now. We have seen that, that is the characteristic. So eddies of different sizes are involved, and because of the interaction between the eddies, so eddies will be there of different sizes, which are going to be there everywhere in this. So because of the interaction between the eddies and the flame zone, a conical flame which is now well behaved in the laminar regime like this becomes convoluted, that is complex. So you can see that the eddies react on this, and you can see some oscillations in the flame zone. So a flame which is conical in shape like this, acted upon by the eddies, it will be like this. So with time this is going to change. So in one time instant it will be like this, in one on another time instant it will be like this, another time instant it will vary. So there will be fluctuations on this. So the in this case what we are assuming is this is a very thin reaction zone. Eddy size is not like smaller than this. So in this case the surface is distorted like this. So the conical premixed flame becomes convoluted, and this is laminar. This is T equal to 0, turbulent as onset. So T equal to 0, I will say T1 and T2, T3. At different time instant you will see different flame shapes, and the surface is not smooth enough, and there is no conical shape at all in this basically. So this is what we are going to get when there is an interaction between the eddies in the turbulent flow, which are of several length scales, and the flame zone itself. So that is the this. So the regimes of turbulence. Okay, now only this can happen or anything else can happen. That will be dependent upon several things. For example, if we are talking about a thin flame, okay, thin flame, that means the reaction rate is very fast. So you know that the thickness of the flame is inversely proportional to the laminar flame speed. So if the reaction rate is very fast, then the laminar flame speed is expected to be higher. So the flame thickness is very thin, like it's very low. So when you talk about thin flames, basically the size of the lowest eddy, the smallest eddy, that is the Kolmogorov scale, can be lesser than this. Can be higher than this flame thickness. In that case, the flame will not be affected by the eddy coming into the reaction zone. So several factors affect this. So magnitude of the reaction rate, that is very important. Then the magnitude of the turbulent intensity and the length scales. These are the things which will affect the flame. So when the flame is going to be affected by this, you can see that the eddy size, the reaction zone thickness, if it's slightly increased, eddy can penetrate that, and so on. So a lot of things will be there. So we get different regimes of turbulent premixed flames. Different regimes we get. So what are they? We will see. Okay. So now first we will consider for the same thing we will try to extend and see the same case of conical flame established over a Bunsen burner we will take, and here the reaction rates are assumed to be much higher than the turbulent mixing rates, so that the flame zone is very thin and the eddy interact with the flame zone without going inside the flame zone. That is what this regime is. Anyway, we are going to come back and name this regime later. So in this regime what happens, we will see this. So these are the this figure shows the convolution of the laminar flame, that is the initial conical flame, basically initial conical flame now due to the eddy interaction becomes so we will get in one time instant. So instantaneous flame images are given here. At one time instant you get like a flame which is convoluted like this, acted upon by the eddies. Similarly, different time instants we will see, and you can see that this boundary here, this boundary and this boundary will be the boundary which will include all the flame oscillations. That means the flame will be extending only within these boundaries. So this is a thick zone, the thick zone which is due to the so this is average, time averaged thing. So at a particular time instant you get a reaction zone which is thin, and when you do the instantaneous flame photograph continuously, you get several instantaneous flame images, and when these flame images are time average, you get this thick flame. So this thick flame is nothing but the time average flame image, and that bounds all the instantaneous images. Okay. So we start with the thin reaction zone which is laminar, and try to increase the velocity of the mixture so within the particular range, so that the diameter of the burner and the velocity, so that the Reynolds number exceeds the value, and the turbulent flame establishes, and try to use a high speed camera, because the fluctuations are of say if there are low frequency fluctuations, then we need to capture that. So that is what high frequency fluctuations, we have to capture that. So we need some extremely, say for example we can go for say 1000 frames per second, something like that. So in order to capture the variations, so high frequency fluctuations we can capture, and we get instantaneous flame images, several of them. And if you try to complete a cycle, then we can see that after a particular cycle completed, again the flame will start oscillating between this and this. So the minimum flame extent will be this part, okay, and the maximum flame extent will be this, and within this the flame will be oscillating. When you take an average, you will see this will be the flame shape of that. So superimposed instantaneous flame images will contribute to a time average flame image, so that will bound all the instantaneous images. So the time average represents the thick reaction zone. Why this has become thick? Because of the eddy interaction. Okay. So that means that when I say this is the time average image, I say that the reaction zone will be anywhere in this region. So in the region what I have plotted in the dark boundaries, the flame can be anywhere in the region. So that's what. So that represents a thick reaction zone. Okay, where eddies contribute to the mixing and the reaction process over a given period of time. So now what happens? This is the laminar flame, the laminar cone. Okay, laminar conical flame. So now there is a particular flame velocity for this. Say by say alpha, I know u into sin alpha will give the SL. So SL can be found. That is the laminar flame speed. But in this case what happens, you can see the for the instantaneous image, the surface area of the flame has increased. Okay. Now coming back to the laminar case, I can say SL will be is what is nothing but the volumetric flow rate of the reactant divided by the surface area of the flame. Okay. So this is, so here also we can see that the surface area in this turbulent case of the flame has increased significantly. So a conical surface has become like this. So it has actually become wavy and enlarged and so on. So effectively the surface area of the flame has increased several times. So here the turbulent flame speed will be equal to the volumetric flow rate of the reactant divided by the surface area of the flame. Okay. So now we can see that the ST will be much greater than SL. So the effect of the turbulence is to increase the laminar burning speed. That means you can see that the flame can now consume more reactants. So that is what the consequence of the turbulence here. Okay. So when you have a conical flame which is well behaved, you have a different given surface area, and the flame when it interacts with the eddies of several sizes, you get different flame shapes and they are not conical anymore. But when you measure the surface area, that is much higher than the surface area of the cone what we got in the laminar regime. And when you divide the, so here also I can say put turbulent this, but when you can see easily that when you calculate the flame speed by using the we can see that this ST is seen to be much higher than SL. So when you calculate the surface area, volumetric flow rate, this is meter cube per second divided by the meter square. So this will be the SL. So this is small, and we can also do it by the U sin alpha of the half cone angle. But if you take the turbulent burning velocity, you can see the surface area has increased by this, and the volumetric flow rate also is higher, much higher, to cause the turbulent flow. So this turbulent burning speed ST is much greater than SL. So even though the surface area is higher, because the volumetric flow rate is much higher now. So this means that the flame can now consume more reactants. So that is what this means. So we have correlations for ST by SL ratio. We have a lot of correlations for this based upon the regime. So the summary here is we can see that the turbulence causes in a thin flame zone. Taking the thin flame zone, the turbulence causes interaction outside the flame zone, basically from the outside the flame zone. They cannot penetrate, the eddies cannot penetrate the flame zone, and we can see that the conical flame is now convoluted to different shapes with increased surface area. And when you take instantaneous time, you will see that variations are there in the flame shape with respect to time. And when you take a time average, it will represent a thick flame zone in which at any time instant we will have a flame within this particular zone. So this thick flame zone will have eddy interactions basically. So there will be eddy inside this and outside this also. So these instantaneous flame zones basically are called flamelets, laminar flamelets. Okay. Now when you talk about the surface area of the laminar flame is much smaller than the convoluted flame, which is actually very larger. The surface area is larger. So now you can calculate the laminar flame speed like volumetric flow rate of reactant divided by the area of the flame. That will be basically higher for this turbulent case, because the volumetric flow rate what we use is higher to increase the Reynolds number. So this is much higher, and even though the flame area is increased, you can see that the ST will be much greater than SL, giving an idea that this turbulent reaction zone will consume more reactants. Then we go for the regimes basically. So the instantaneous flame, as I told you, the instantaneous images what we have shown is relatively thin, and it represents a laminar flame basically, because till that point when this very extremely thin reaction zone which is having a length scale lesser than the lowest the smallest length scale of turbulence. So then eddies cannot penetrate the reaction zone. So this thin flame reaction zones can be called laminar flamelets. So that we have to understand, laminar flamelets. So that is, the laminar flamelets are the reaction zones which are not affected by the eddies which is penetrated inside the. So only outside the flame laminar flamelets eddy can be prevailed. So the laminar flames are thin reaction zones where there is no influence of eddies basically. But based upon the size of the reaction zone, we have several regimes. So that we will come upon now. Okay. So the regimes of the premixed turbulent flames can be understood by comparing the laminar flame thickness delta with the turbulent length scales. So that is the simplest things we will do. So for example, the regimes are presented here. So we will actually see three regimes basically by what was observed by the several researchers. The first regime is called Wrinkle laminar flames, in which the flame thickness, laminar flame thickness is less than the smallest length scale. This is the Kolmogorov scale. Okay. So now you can see that when the flame thickness, the extremely fast reaction take place and the flame thickness are very small, which is less than the smallest eddy size what we have. So that means that if this is the flame zone and the eddies are larger than this. Okay, so this the eddy sizes are larger. This is LK and this is the delta. So now delta is less than or equal to LK. So that means that the eddy cannot go into this, penetrate into this, and because this the flame zone is, the reaction zone is extremely fast, because eddy length scale is larger than that, it cannot penetrate there. So in this case, eddy can only act outside the surface of the flame. So that will form what is called the wrinkle laminar flames. That is what we see here. Basically, eddies act upon this flame zone, conical flame zone, make it convoluted like this, and this changes with time, and we get a thick flame zone finally. Now in the second regime, we have flamelets in eddies. So now what happens is the Kolmogorov scale is now smaller than the laminar flame thickness. So now we have a slightly thicker delta here, that is delta, and Kolmogorov scale is smaller now, LK. LK is smaller, so LK can go into this eddy can be inside. Okay, so this is the LK. So this can go inside now. The smallest eddy can penetrate into the flame, but this integral scale, okay, turbulent integral macro scale cannot penetrate. That means that a lot of bigger eddies still remain outside. The smallest eddy can now penetrate. So this is the regime where L0 is greater than del, which is greater than del is greater than LK. That will contribute to what is called flamelet in eddies. Let us see that later, how it will look like. Then the third is the distributed reaction zone. Now you can see that del is even greater than the turbulent L0, the integral scale. Okay, del is greater than L0. So these are the regimes which will tell us whether the turbulent eddies will penetrate into the reaction zone or not. So in the first case, there is no penetration of the eddy inside the extremely thin reaction zone, and only the surface convolution happens for the flames, laminar flames. So that anyway we can see that there is an increase in the burning speed, rate of consumption of the reactants and so on. Second is the flamelets in eddies. Here the problem is part of smaller range of eddies can penetrate into the reaction, but there are again larger eddies which cannot penetrate. But if you go to distributed reaction zone, the flame thickness is higher than the integral scale itself. So the L lambda will be somewhere in between this basically. Okay, so the Taylor's microscale. So based upon the comparison of the laminar flame thickness del and the turbulent length scales like LK and L0, we have three regimes for the premixed flames in the turbulent regime. Three separate regimes we have. So we will go to see how they are going to be, what are the characteristics they have. So before that, we will also introduce the Dam-Kolar number, which we know it's very important characteristics and non-dimensional number for us, which is we know that it's the ratio of the characteristic flow time to the characteristic chemical time. So that we know already. Now chemical time in this scenario can be defined as what? The flame thickness, laminar flame thickness, and this is the laminar flame speed. Okay, so this ratio will be the tau c, chemical time. Now, how will you calculate the flow time? So, for since turbulent flow involves eddies of several sizes, So, for example, based upon one length scale, you will have one time, characteristic flow time. So, multiple time scales are associated, correct. So, the turbulent macro scale or the integral scale, let us use that to calculate the flow time, and the velocity will be the RMS value. So, L naught by V dash RMS, this is the RMS value of the fluctuation. If we take this as the flow time, then the Damkohler number can be put as a ratio of the flow time by the chemical time, that is L naught by V dash RMS divided by del by SL. Okay. So, the flow time, this is the flow time, and this is the chemical time. So, we can write like this, but we can also write the Damkohler number as L naught, the ratio of this, which we have already seen, the ratio of the turbulent length scale to the laminar flame thickness divided by, so here V dash RMS divided by SL. Okay, you can see this turbulent length scale divided by the laminar flame thickness divided by the turbulent intensity divided by the laminar flame speed. So, this is also Damkohler number. So, both ways you can write this. So, based upon the value of the Damkohler number, we can define the regimes. So, in the previous slide, the based upon the comparison between the flame thickness, laminar flame thickness and the length scales, the regimes are defined. Now, the same thing can be done with the value of Damkohler number also. We can see Damkohler number is nothing but the flow time, which is the integral scale by the turbulent intensity divided by the laminar flame thickness divided by the, this is the chemical time, laminar flame thickness divided by the laminar flame speed. So, this can be written as a ratio of the length scales and the velocity scales. Okay. So, now based upon that, we will try to understand the consequences. So, let us first say the reaction is infinitely fast. So, Damkohler number will be much greater than 1, correct. So, reaction rates are faster than the turbulent mixing rates. So, when I say reaction rate, say please understand, it is called volumetric reactions contributed by the mechanism what we have, correct. So, it may be the single step mechanism, or it may be a chemical mechanism with the chain reactions, elementary reactions and so on. So, but when the set of reactions what we use are faster than the turbulent mixing rates, then in this case Damkohler number will be greater than 1. Okay. Now, when the reaction rate is assumed to be infinitely fast, okay, very reactive species, and the flame speed is very high, the reaction zone is extremely thin, and now we have the Damkohler number much greater than 1. The extreme cases, other opposite cases, the turbulent mixing rates are much higher than the reaction rate, then Damkohler number will be much smaller than 1. So, this we can easily understand by the equations what we have written. Similarly, what I have told is same thing, Damkohler number can be written as the ratio of the length scale of the turbulent and the laminar flame thickness as to the relative turbulent intensity. So, V dash RMS by SL is called relative turbulent intensity. Normally, relative turbulent intensity can be written as V dash RMS or U dash RMS divided by U bar, mean velocity. Now, since U bar and SL are connected, okay, SL is a function of U bar, I can say this V dash RMS by SL as the relative turbulent intensity. So, we can also define like this. Okay. So, basically we can draw maps in this coordinate and try to see where the turbulent premixed flame regime will lie. Okay, that we are going to do it eventually. So, now if the length scale is fixed, okay, then the Damkohler number decreases as the turbulent intensity is increased. This intensity is increased, that will decrease because this is the ratio, correct. So, L naught by del divided by V dash RMS by SL. So, when you fix the length scale, when the turbulent intensity increases, then the Damkohler number will decrease. So, that will contribute to this regime, okay, where the turbulent mixing rates will overtake the reaction rates. Okay, now turbulent intensities, how they will increase? They depends on the turbulent Reynolds number. As the Reynolds number increases, then the turbulent intensity will increase. So when you set a problem, then the length scales are almost set. Okay, so basically we are talking about the L0, so that will also be almost the same. So once you have a chamber, everything is defined, then the length scales are pretty much fixed. So when you increase the Reynolds number, then you turbulence Reynolds number, basically you increase the turbulent intensity. So we move from the reaction rate control to the turbulent mixing control regime. So that is what you have to understand. We will see more on this. Okay, now what is laminar regime? See, everything is basically is turbulent. There is some length scale which may be smaller, etc. There may be some small oscillations present in the field, etc. So based upon this, when we have this length scale ratio L0 by del or the relative turbulent intensity V dash RMS by SL less than 10, then the flame will behave as a laminar flame, phenomenally as a laminar flame. So this is also one of the important things which we should understand. Okay, so these are the things. So once you define the Damkohler number like this, we can understand several regimes based upon the values. Basically, we are trying to attempt exercise where we will compare the L0 and del and the V dash RMS and SL and try to come up with the regimes. Okay. So let us go into the three regimes in slight detail. So first one is the Wrinkle flame regime. So now V dash RMS by SL is so in Wrinkle flame regime, SL is very high. Correct? We are talking about high reaction rates. So high values of SL. So what happens when high values of SL prevail? The flame thickness will be extremely thin. So thin flame. So I am saying about this thin flame and the SL is being high. So this ratio is less than 1. So now once you fix this intensity, relative intensity, then for a wide range of length scale ratio which is greater than 1, okay, this is L0 by del greater than 1, we will say, because already you can see that del is smaller. So this is actually greater than 1. So for a ratio, for a range of these values of this ratio, you get what is called the Wrinkle flame regime. Basically because the smallest eddy cannot penetrate the flame and they act upon this, and the flame surface area is now increased. You can see this will be surface area now, this into say the in-depth whatever be the width, that may be taken as the surface area, but here you can see that the flame is convoluted because of the action of these eddies. So this eddy acts and pushes the flame like this eddy acts and pushes the flame like this, and so the wrinkling of the surface takes place and surface area is increased. So now the reactants are consumed at a faster rate in this particular thing. So you can see that here the burning velocity will be normal to this surface, but here you can see that burning velocity changes the direction, etc. like this. So they are normal to the surface, where the surface itself is now convoluted. So you can see the surface, due to the increased surface area, more reactants are consumed. So volumetric flow rate which is taken in is higher. So the flame speed increases. So in this regime, obviously we have already seen that the Damkohler number will be much greater than 1. The eddies are larger than the reaction zone thickness and the reaction rates are much faster. So to repeat the same thing what we have seen. So now eddy cannot penetrate the reaction zone, flame surface becomes wrinkled only. So that is only the like increase of surface area of the flames, and so the consequence is the increase of surface of the flames, not any change in the reaction zone. Still the reaction is controlled by the reaction rates, the mechanism what we have. The eddies cannot control the reaction rates because they are slower. So wrinkling causes an increase in the overall surface area of the flame, as I told you, and thus the turbulent flame speed ST increases. So normally you can see that the ratio of the turbulent flame speed ST divided by the laminar flame speed SL will be a function of the relative turbulence. As this increases, this will also increase. So when you fix the time length scale, when the turbulent intensity increases, the flame speed will increase. So this is the so a lot of correlations are available based upon this function. So a lot of correlations we can write. So, in the Wrinkle flame regime, which is the regime where Dam Coulomb number is much greater than 1. So, here also we have seen this infinitely fast chemical kinetics, Dam Coulomb number is much greater than 1. So, that regime will not have will not have the eddies to penetrate into the reaction zone, and the reaction zone are still controlled by the chemical mechanism. And the action of the eddies is to increase the surface area of the flame in order to make it consume more reactants. So, that is the first regime. Second regime is called flamelets in eddies.